Okay, so welcome to the 20th video in the Discrete Structures series, and this video is going to be a start of a new chapter, Logic and Proof Methods. And this is the chapter where we study formal logic, which is the foundation of Boolean algebra. So we'll be covering this in a lot of detail. And in this particular video, we'll discuss the idea of propositions and propositional logic. And inside of this, we will look into simple and compound propositions, and we'll look into the different ways of combining propositions. And within this, we'll look at negation, the connectives conjunction and disjunction. And after that, we'll have a quick look at the idea of truth tables. And then we'll have a look at a compound operator named XOR, and this is called exclusive OR. And then we'll resume our session in the next video with a discussion on implication, the converse, inverse, and contrapositive. Okay, with that overview, let me get started with the first topic of propositions. So proposition is any statement or declaration that can be resolved to being true or false. So most of us must be familiar with this, so we'll go through this quickly. I'll just set a couple of examples and we'll look into those. So let me write a few statements. Okay, so I put some statements in the board and we'll try to see if each of them are propositions, and we'll also try to resolve if they are true or false. So first we inspect if the sentence is of a type that can be resolved into a true or false in the first place. And if that is the case, it is a proposition and therefore its value would be resolved into a true or a false. So let's see this one. Sun is bigger than Earth. So this can be resolved into true or false. So this is a proposition. Okay, it is not about the facts that we know. In the ancient times, people believed that the Earth was much larger than the Sun, and the Sun was something that revolved around the Earth. But even in that time, this would be a valid proposition, because by nature, this requires an answer in the nature of true or false. So I think that's quite easy of a concept to grasp. So let's get through this quickly. Looking into this one, there are more than 1,000 countries in the world. So I can see that it is proposing something. It can be resolved to a true or a false. So this is a proposition, and in this case, this is a false one. Okay, so this is a proposition, but it resolves to false. What about this one? This is a proposition because it's simply proposing that the sum of 1 and 1 is 2, which is true. And moving over to this one, 2 plus 2 equals to 3. This is also making a statement that can be resolved to a true or false. So this is also a proposition, but its truth value is false. Okay. Now if we look at these sentences, I think it's easy to rule this out. This cannot be resolved as true or false. We are not saying that this sentence is false. Okay. That is a different thing. We are saying this is not even a proposition, because this kind of statement cannot be resolved as being true or false. Read this carefully. Same thing goes here. It cannot be resolved. What do you think about x plus 1 equals 2? Well, this is also not a proposition because it cannot be resolved. But if I add something like, let's say x is equals to 3, once I add this becomes a proposition and a false one, because substituting 3 here breaks this equality. Okay. Therefore, if I mention this in conjunction to x is equals to 3, this becomes a proposition and a false one. But if I only mention this thing, this is not a proposition because it cannot be resolved into a true or false. And same thing goes here. Without any specific values for x, y, and z, I cannot tell whether this is a proposition. And you should know one trivial fact. Propositions are generally denoted with lowercase letters starting from P. So P, Q, R, S, and so on. Okay. And the truth values for propositions are generally denoted by T for true and F for false. It is also accustomed to write 0 and 1. And the branch of mathematics that deals with the propositions and their truth values is called propositional logic or propositional calculus. And it has major applications on automated reasoning. If you don't pay your electricity bill, you will get fined. But these days, that process is completely automated. The point is that we are able to design systems that can automate a lot of reasoning and logical tasks. So propositional logic is a foundation for automated reasoning, which in turn is the foundation for Boolean algebra and basically all of modern computing. Okay, so the topic that we are learning here is really important in that regard. Okay, and that said, we'll move on to the next topic now. Compound propositions. So compound propositions can be defined as propositions that are formed by combining two or more simple propositions. So simple propositions are ones of the type that we already discussed in our earlier segment. So it's basically any proposition that can be immediately resolved into a true or false without depending on any other proposition. But a compound proposition depends on the truth value of simple propositions and how they are combined in order to determine whether they will be true or false. So let me demonstrate that with an example. And we will do that by exploring different ways for combining propositions. The first one is negation. And if a proposition is denoted by P, its negation or complement is denoted by P complement or not P in this way. Throughout this chapter, we'll prefer this one. And let me write a couple of quick examples for demonstration. Okay, so I put 3 statements here. All of these are propositions and we'll try to see what each of these look like when negated. So the negation of my PC runs Linux would simply be my PC does not run Linux. So this was a simple one. Now let's see what this sentence is saying. Originally, this sentence is claiming that I have at least 5 pens, okay? So I could have 5, 6 or any number that is greater than 5 because that is the definition of at least 5, right? That means 5 or more. Therefore, its negation would mean I have less than 5 pens. And here by less, we mean strictly less, okay? And what would the negation of this be? Some of us may be tempted to write x plus y is less than 5, but this would in fact be wrong. The negation of this is x plus y is less than or equal to 5. Because the negation needs to cover the entire space of possibilities except this one. Since this equation entails a possibility of x plus y being greater than 5, this has to cover both possibilities of being equal or less than 5. Okay, so the second way of combining propositions is by taking a conjunction, and it is denoted with this symbol in propositional logic. And this is the same as a logical AND. A conjunction is true if all of its composing propositions are true. So we will not be spending much time discussing this. And similarly, like conjunction, we have the disjunction, which is denoted by this symbol. And this is also equivalent to logical OR, meaning a disjunction of a number of propositions is true if at least one of them is true. So negation, conjunction, and disjunction are 3 basic ways of combining propositions. Next, we'll be looking into exclusive OR. But before that, let's have a quick look at truth tables. Alright, so given any proposition, simple or complex, a truth table outlines all the possibilities for that proposition to be true or false. So let me write a very simple proposition here. I want to write not P. And given P is my original proposition, I want to see the cases where not P is true and cases where not P is false. So I do that by constructing a truth table which lists all the possibilities for P and explores the corresponding values for not P in all those cases. The proposition that I have written here contains only one variable P. Therefore, I only have to list the 2 possibilities of P being either true or false. And by definition, when P is true, not P should be false. And when P is false, not P should be true. And so what we have constructed here is called a truth table for not P. Let's also construct one for the conjunction of 2 variables. Let's say P and Q. And the point I want to demonstrate is, here I am using 2 variables P and Q. Therefore, there will be 4 possibilities. With one variable, I only had to check when it was true and false. But here I have to check both possibilities of P with both possibilities of Q. And that gives 4 total possibilities. So we list them here. P and Q are my inputs. And I'm going to look at the value of P and Q. And the way you list the truth values here is analogous to binary counting. That is because counting in binary in 2 digits, for example, gives me all permutations of 0 and 1 in 2 digits. So I mean to say I have 0, 0, 0, 1, 1, 0 and 1, 1. And I'm counting from 0 to 3 in 2 digits. And you can see this lists all the permutations of 1 and 0. So this is a convenient analogy to list truth values in this table. And let's assume 0 is a false and 1 is a true. Then my truth value permutations would look like this. And since we are taking an AND operation, this is true here and false in other cases. Okay, so this table is for P and Q, and I think you can similarly construct one for P or Q. And as the chapter progresses, we'll be drawing many truth tables anyway, so I'll leave the discussion of truth tables here. Next, let's have a look at one another operation, and that is XOR or exclusive OR. And there's a pretty neat trick to remember the truth values for an XOR operation, which I'll tell you shortly. Let me first draw the XOR truth table for 2 propositions, P and Q. Okay, so this is what an XOR truth table looks like. And we should go to the definition of exclusive OR in order to understand and to be able to generate these values easily. Okay, so an exclusive OR is basically saying exclusively OR. And it is funny that many people find exclusive OR confusing, but the OR that we use in common English and real life is almost always exclusive OR. Okay, so let's say my choices for vacation are Nepal, India and China. The OR that we learned recently allows both of these values to be true. When I'm saying I'll go to vacation to Nepal or India or China, I do not mean OR in the usual sense of disjunction as we learned earlier. Because that OR would allow a situation to be true where I went both to Nepal and India. And even China for that matter. If I went to all those 3 places, that OR would still be satisfied. But in real life, when I'm mentioning that my vacation choices are Nepal or India or China, I'm mentioning that I'm exclusively going to one of those places. So you should remember exclusively OR as being true when exactly one of the items is exclusively chosen. And that applies to any number of variables. If I have P, Q, R and S and I need to make an exclusive OR choice, exactly one of these need to be true and remaining 3 need to be false. And that is the case when the exclusive OR would be true. In other case, it would be false. And now you can see that the same thing is happening here. Here I did not make any choice at all, so this is false. Here I made an exclusive choice, only one is true, so it is true. This is also true because I made an exclusive choice, because this is true and this is false. So exclusive OR here is true. But in this case, I made two choices which I'm not allowed to do. I did not make an exclusive choice, therefore this is false. And the same reasoning is even powerful when you need to compute this for 3 variables or 4 variables, like for example. Okay, so that is the discussion for this video. We'll start next video with a look at implication and also the ideas of converse, inverse and the contrapositive. So I'll see you guys in the next video. Until then, have a good day and bye.